Hello everybody, I hope you had a nice weekend. We're back to chapter 7.4 today. We're just finishing up our chapter on acids and bases. We've got our test coming up later on this week, and I want to pick up where we left off on Friday. So on Friday we finished section 7.3, and I left you with a bunch of questions here on page 264, so I want to take a few minutes and quickly take up that homework before I move on to 7.4, which are chemical reactions involving acids and bases. Okay, so let's go to the textbook, page 264, and we start here with these questions. So we have questions 1 and 2. So it says define the acid and an acid or a base according to the modified Arrhenius theory. Now I'm going to go back because I think it's important to look at the two, the original theory for acids and bases and then the modified theory. Okay, so Arrhenius basically said our definition for an acid is something that when we put it in water, it releases hydrogen ions. Plus something else, but I don't care about the something else. All I care about are hydrogen ions. And Arrhenius said something is a base when it contains hydroxide ions. So that when I put it in water, it will release the hydroxide ions. Again, plus something else, but I'm really only interested in the hydroxide ions. That's what makes it a base. Now, if I scroll up here, it says an acid is a substance that ionizes in water to produce one or more hydrogen ions. Right, so there it is up there. A base is a substance that dissociates in water to release one or more hydroxide ions. So there it is there. But then again, remember we had some things that didn't work, like ammonia, which is a base, because I know when I put it in water it will produce hydroxide ions, but it doesn't contain any hydroxide ions. The reason why it makes hydroxide ions is because it will steal an H plus from water. It will steal a hydrogen from water to make NH4 plus and leave the OH minus for the base. And the other part of the issue with the Arrhenius model was that this thing really doesn't exist in water. So when I put my HCl in water, right, the H plus will actually bind to the water to make H3O plus, right? And the H3O plus is the hydronium ion, right? And that's what it is that makes something an acid. Because this doesn't exist in water, as soon as I put the two of them together, they will create that hydronium ion. So technically, we do have H pluses being created, but they won't stand alone in a solution. So we had to modify our two definitions. Our definition of the modified Arrhenius theory says an acid is a substance that reacts with water to produce hydronium ions. And a base is a substance that dissociates in water or reacts with water to make hydroxide ions. So those are our two definitions that we're going to be using for acids and bases. Okay, question 2 from the homework. Oops, come on. There it is. It says use a chemical equation to show how hydrogen nitrate, which is nitric acid, fits the definition of an acid according to the modified Arrhenius acid theory. So I need to be able to write a chemical equation to show how this will produce hydronium ions. So if I take my hydrogen nitrate and put it in water, my products will be the H plus here will join the water to make a hydronium ion, H3O plus, and it will leave behind the NO3 minus. So the hydrogen nitrate separated into a hydrogen ion and a nitrate ion, but the hydrogen ion doesn't work on its own. It will see a water and it will bind to the water to make H3O plus. Right? So there's the chemical equation that shows how nitric acid or hydrogen nitrate will react with water to make a hydronium, H3O plus, which is our modified Arrhenius theory for an acid, or definition for an acid. Okay, down to question 5. It says distinguish between a strong base and a weak base in terms of how much they dissociate. So I've got 2 bases here. I want to look at sodium hydroxide. Oops. Let's put sodium hydroxide and let's say copper 2 hydroxide. And the question is, which is a strong base and which is a weak base? Remember, the strong bases are the ones that contain alkali metals, the group 1 metals, right? So that would make it a strong base. This is not a group 1 or group 2. So group 1s and group 2s make strong bases. These do not. Now, the question says, in terms of how much they dissociate, when I put this one in water, it's a strong base, it will separate 100% into sodium ions and hydroxide ions, Na plus and OH minus. When I put this one in water, some of it will separate into copper 2 plus ions plus 2 hydroxide ions. But it's a weak base, so probably less than 1% of this will actually become ionized. Most of it will stay as copper 2 hydroxide. It will not release a lot of hydroxide ions. So that's our definition. That's our difference between a strong base and a weak base in terms of how much they dissociate in solution, how much they will separate into sodium ions and hydroxide ions. 100%. It's a strong base. Copper ions and hydroxide ions, almost none at all, because it's a weak base. Okay, so that's the main difference between the two. Question 6 asks for an example of a weak acid and a strong acid, and a weak base and a strong base. Strong acid, hydrochloric acid or hydrogen chloride is a really good example of a strong acid. A strong base is a group 1 base or a group 2 base, like maybe calcium hydroxide. A weak acid would be maybe the one that we've got so many here. How about H3PO4? Right, there's one. There's so many. We're going to actually be doing a lab tomorrow, so I'm actually going to use the acid that we're going to use in our lab, which is HC2H3O2, which is vinegar. It's acetic acid, and it's a weak base. Right? If it was a strong base, we wouldn't be putting it on our potato chips to have salt and vinegar potato chips, or are we putting it in our salad dressing to have oil and vinegar dressing? If it was a strong acid, it would damage our body, right? But a weak acid is not that dangerous. And a weak base, there are so many. Ammonia is actually a weak base, but so would be the one that I just looked at a moment ago, which was copper 2 hydroxide. So there's an example of a weak base. Right, copper, not calcium, that's copper, Cu. Okay, so some strong acids. Again, there are thousands and thousands and thousands of weak acids and weak base, and probably only a handful of strong acids and strong bases. Another good strong acid might be HNO3. Again, we use that a lot in chemistry. So HCl and HNO3 are 2 very good examples of strong acids. Okay, if I continue down, that's question 6. It says go down to question 9. So question 9 it says, how are the concentrations of hydronium ions and hydroxide ions in a solution related? Describe what happens to one as the other one increases or decreases. So I'm going to go back in my notes to a graph that I kind of skipped over, which is this one here. Okay, this one shows how much hydronium ion there is in pink and what the concentration of hydroxide ion is in blue. So for a neutral solution, which is right here, right, I can see that I've got as much pink as I have blue, right? Equal amounts of hydronium ion and hydroxide ion. They are both present in equal amounts in a neutral solution. If I look way down at this end over here, I can see that the amount of pink is huge. It's 100%. The amount of blue has dropped off to 0. So for a strong acid, I have a lot of hydronium ions and none of the hydroxide ions. If I go to the opposite end of the spectrum, way over here, I can see that I've got a lot of blue, right? Almost 100% is hydroxide ion, and the amount of hydronium ion, the pink, is almost gone by the time I get to a strong base. So in all solutions in water, all solutions will contain both the hydronium ion and the hydroxide ion, but the amount of them, the way the relative amounts of the two of them decide whether it will be an acid, base, or neutral, and how acidic or how basic the solution is going to be. Okay, so there's question number 9 from the homework. Question 10 shows some pH paper. Again, in a regular time, we would have done a lab where we would have used pH paper. And with pH paper, it's kind of like litmus paper, except we dip it into a solution and it turns any of a number of different colors. So you can see the whole range of colors in here. So I've dipped my paper in and it's turned this kind of bluey color, which is probably telling me that the pH is probably pretty close to pH 10. Maybe 9, but probably closer to 10 by the looks of it. It hasn't got too much green in it. So I'm going to compare it to the color chart, color wheel there, and it will tell me what the pH is. So the question says, what is the pH, and is it an acid or base? Obviously it's a base. It says why? Because the pH is greater than 7. Right, and that's all there is to it. Okay, question 11 says use the pH scale to define the following terms. Again, we know that if it's an acid, the pH is 0 to 7. If it's a base, the pH is 7 to 14. And if it's neutral, it's right on 7. That's it for question 11. Okay, question 12 says arrange the following foods in order of increasing acidity. Right, so I'm going to have to finish with the most acidic one, right, which would be that if I'm looking at my different foods, I'm seeing beets are 5, this camembert cheese is 7.4, the egg white is 8, sauerkraut is 3.5, and yogurt is 4.5. So I'm going to start with the one that's 8, which is my egg. Oops. So I'm going to start with my most basic one, which is the egg, which is 8. I'm going to move down to the cheese, which is 7.4. I'm going to move next to my beets, which are pH 5. The yogurt, which is pH 4.5. And then the sauerkraut, S-A-E-U-R, is the most acidic. Okay, so in order of increasing acidity, this is the highest at this end, this is the least at this end. And the last question from the homework was question 13, and it says the pH of normal rain is about 5.5 because you think, well, that's an acid, right? Why is rain acidic? It's acidic because there's carbon dioxide in the air. And as the carbon dioxide in the air, it turns into a weak acid in the rain, carbonic acid. And when it comes down, it makes the rain a little bit acidic, pH 5.5. That's not very acidic. It says consider acid rain that has a pH of 3.5. Okay, so there are places in the world where there's a lot of industry, a lot of chemicals go up in the air, and it makes the pH 3.5. And it says, how do the hydronium ion concentrations in these two compare? Right, notice the difference between this pH here and this pH here is 2 pH units. Remember, every pH unit means times 10. So to go from 3.5 to 4.5, it would be times 10, and to go from 4.5 to 5.5 would be times 10 again. So this one here is, this one here is 100 times more acidic than this one here. Right, the 3.5 is 100 times more acidic because from 3.5 to 4.5 means times 10, and from 4.5 to 5.5 means times 10 again. So I need to go 10 times 10. Okay, so that gets us through some homework and just gives us a chance to be talking about acids and bases. Now today I want to look at a chemical reaction that happens between acids and bases. And that's called a neutralization reaction. So in a neutralization reaction, I always start with two reactants. Remember, it's a chemical reaction, so I need reactants. They are an acid and a base. So let's just use an example here. Hydrochloric acid and sodium hydroxide. Notice this one here is an acid because it starts with H. This one is a base. It contains hydroxides. Now, not all bases do, but as soon as I see the hydroxide there, I know it's a base. So what's going to happen here is a double displacement reaction, where the hydrogen is going to kick the sodium off, and the sodium is going to replace the hydrogen. So the hydrogen will join the OH to make HOH, which is water. And the Na is going to replace the H to make NaCl, which is an ionic compound. In chemistry, we use this word salt to represent not table salt, but any ionic compound. Right? That's what our definition is for a salt. So there's a salt there. That just happens to be table salt. This is a salt too. You don't want to put that in your mouth, right? That would be bad. Right? It's potassium nitrate. So the reaction says whenever an acid reacts with a base, I'm always going to get water and some ionic compound, right? Which we're going to call a salt. So, okay, so that's our basic formula. Acid plus base makes salt plus water. Like I said, it is a double displacement reaction. As we've just seen, the hydrogen replaces the cation, the positive ion, on the hydroxide to make H2O, and that positive ion replaces the hydrogen to make the salt. Same thing here. Hydrogen replaces potassium, potassium replaces the hydrogen. So I get KNO3 and HOH, or water. Right, so we always get salt plus water. And we always start with an acid and a base. So that's what a neutralization reaction is. It's a type of double displacement reaction. Now, in both of these cases here, notice that HCl is a strong acid and HNO3, they're the two that we actually just used in the homework to describe strong acids. And NaOH and KOH are both hydroxides of group 1 metals, so they're both strong bases. So again, just when I put my strong acids and strong bases. Remember, our definition for a strong acid or a strong base is something that will dissociate 100%. Right? All of it will separate into its ions. Now, what I'm going to have here is if I have equal amounts of the acid and the base, then they will, according to our mole ratios, I have a 1-to-1 ratio, so the resulting solution is going to be neutral because I'm going to use up all of the H+, all the hydronium that's produced, and all the hydroxide will cancel each other out and turning into water. If I have an excess of the acid, in other words, more acid than base, then all the base will be used up, consuming acid, but there will be acid left over, which means the solution will be acid. If I have more base than acid, then the acid will all get used up, neutralizing some base, but then the acid will all have turned to water, and I'll have leftover base, so my solution will be basic. So we're going to see here how we can use this now to try and calculate a concentration of something that we don't know. Right? So if I tell you that in this beaker there is some hydrochloric acid, HCl, but I'm not going to tell you what the concentration is. I want you to find out the concentration. Okay, we're going to spend some time in tomorrow's note looking at the procedure for how we would actually do that. Right? So for today, I just want to look at the math. So it says if I know the concentration of either of them, I can use that to determine the unknown concentration of the other one. Right? So if I know my concentration of either the acid, then I can find the concentration of the base. If I know the concentration of the base, I can find the concentration of the acid. So if I know the concentration of either, I can find the molar concentration, moles per liter, of the other one. The video that you're going to watch tomorrow, which walks you through the lab, they use the word molarity. Molarity basically means the concentration in moles per liter. Okay, so I want to look at the first sample problem here. And I'm going to basically write it out the way I would normally write out a chemical reaction, because it's a neutralization reaction. So what I'm going to have is hydrochloric acid reacting with sodium hydroxide. Right? And we're told that we have 13.84 milliliters . I really wish I could get this to work better. Try my other pen. Forever jumping back and forth. 13.84 milliliters. And we're using that to neutralize 25 milliliters of sodium hydroxide. Okay, this is NaOH. So I'm neutralizing acid plus base. Right now, what I'm looking for, it says what is the concentration of the hydrochloric acid. So my C here, is my unknown. And to find that concentration, I need to know the concentration of the other one, which is the sodium hydroxide, and I can see that it's 0.100 moles per liter for my sodium hydroxide. Right. Now, I know that when I'm neutralizing them, okay, what I just said a moment ago is if I have equal numbers of moles of acid and base, then the result will be neutralization. The resulting solution will be neutral. Okay, so that's what I'm trying to have here, is an equal number of moles of acid and base. Now, I can't really calculate anything about hydrogen hydrochloric acid, but I can see that for sodium hydroxide, I can calculate how many moles of sodium hydroxide I have using CV. Now, my problem here is that my volume here is in milliliters and my concentration is in moles per liter. So I'm going to have to calculate how many liters of sodium hydroxide I have. So I'm going to multiply this. Let me undo that. Multiply this times, I know that 1 liter is 1,000 milliliters. So if I do the math, 25 times 1 divided by 1,000, 0.02500 liters. So now if I'm trying to find my number of moles, C times V, I'm going to get 0.1000 moles per liter, that's my C, times the volume, which is 0.02500 liters. Notice that my liters in the denominator and liters in the numerator will cancel, and I'll be left with an answer in moles, which is what I'm looking for because the answer is N, number of moles. So N is going to be equal to 0.00250 moles. Notice that there's a lot of zeros that we're leaving in here, okay, and ultimately all of these trailing zeros here are always important because remember, we're talking significant digits here, so all of those digits, all those trailing zeros are important because it helps me to more precisely determine the calculation, the answer that I'm looking for. So to be as precise as possible, I need to maintain the number of sig-digs, significant digits. I need to leave those zeros in. Okay, so let's get rid of that. Okay, so I now know how many moles of sodium hydroxide I have, but remember, what I'm going to try and do here is I'm trying to find the concentration. Concentration is equal to number of moles divided by volume. Right, number of moles divided by volume. I know the volume. I should actually convert that into liters up there. So volume, I'm going to divide it by 1,000 to get liters. 0.1384 liters. And what I now know is if I have this many moles of base, when I've neutralized it, I will have neutralized the same number of moles of acid. So I'm just going to take this number from here, moles of base, and make it the same as my moles of acid. Okay, so now I can actually calculate concentration, which is equal to N over V. So my C is N, 0.0025 moles, divided by my volume, which is 0.01384 liters. And my C is equal to 0.1806 moles per liter. Okay, and there's my answer. So the question says, what is let's make this smaller. Right, what is the concentration of the hydrochloric acid of HCl? Right, so I'm trying to find the C here for HCl. So notice, like we were doing before, I'm doing all my math in columns under the reactants or products, in this case the reactants, for my neutralization reaction. Okay, I'm going to move up to the second sample here from our textbook. Okay, the second one here, this is what volume of sulfuric acid is needed to completely react with potassium hydroxide. So let's write down our formula here, our equation. So I've got sulfuric acid, H2SO4. Notice it's an acid because there's the H at the beginning there, reacting with KOH. Okay, notice I'm seeing my KOH has got the hydroxide, which makes it a base. Acid plus base, so I'm looking at a neutralization reaction. Now, it says I'm trying to react completely. In other words, I'm trying to neutralize all of the hydroxide. Now, we're told the volume of sulfuric acid. Oh no, it says what volume of sulfuric acid. So my V here, V here is unknown. We're told the concentration of the sulfuric acid, though, 0.250 moles per liter. It says we have potassium hydroxide. The volume is 37.2 milliliters. Again, I know that 1 liter is 1,000 milliliters. The milliliters will cancel, and I'll end up with 0.0372 liters. And we're told the concentration of the KOH is 0.650 moles per liter. So I can see that I know the concentration and the volume for the KOH, so I can figure out how many moles of the KOH N equals CV. Concentration times volume. Let's just do this the way. N equals concentration times volume. I know the concentration, I know the volume, and I'm getting 0.650 concentration times my volume of 0.0372, and I'm getting 0.02418 moles. That's moles of KOH. Now, notice that, remember we said bases have OH and acids start with H. Notice that this has two H's, right? Which means this sulfate here has two hydrogens that it can use, so one of these will neutralize two KOHs, because both hydrogens from here will each require an OH. So my mole ratio now, I need to use mole ratios to figure out my number of moles of acid is equal to my number of moles of base times my mole ratio. Now, let's go back up to the top here and let's write the full equation. So the full equation would say that, notice that one hydrogen will kick off a potassium. Well, let's just look what our product is going to be. Our product is going to be H2O, And notice that the K is going to join the sulfate here. So I'm going to get KSO4. But remember, sulfate is a 2- ion and K is a 1+. So I'm going to take the 2- from here down to the K and the 1 to the potassium down to the sulfate. So I actually get K2SO4. Just like I had H2SO4 over here, I need K2SO4. Notice I now have 2 potassiums on this side. I only have 1 over there. So I now need to start doing some balancing work here, and I'm going to double my number of potassium hydroxides, and now I'm going to get 2 Ks going on to the SO4, so I'll get my K2SO4, but the 2 OHs will bond with the 2 Hs to make 2 H2Os. Now if I double check my balancing now, I've got 2 hydrogens on this side. Oh, I've got 2 more hydrogens. I have 4 hydrogens on the left. I have 4 hydrogens on the right. I have an SO4 on the left. I have an SO4 on the right. And then I have 2 O's here in the KOH, and those 2 O's are there. Right? So it's balanced. But notice that in my balanced equation, I have 1 K2SO4 for every 2 KOHs. So I need to do my mole ratio now down at the bottom of the page here. My mole ratios say I get 1 H2SO4 for every 2 moles of KOH. Right? 1 H2SO4 for 2 KOHs. Right, so now, and then the KOHs will disappear, and I will end up with number of moles of H2SO4. So it's going to be number of moles of KOH, which we just calculated, which is right here, 0.024, right, KOH, 0.02418. Times 1/2. So my number of moles of H2SO4 is equal to 0.01209 moles. Okay, so that's how many moles of acid were neutralized by this number of moles of KOH here. Right, so there's my number of moles. So we're done, right? Well, actually, we're not done, because the question said, what volume did we have? So if I go back to my original formula, remember my formula says volume is equal to volume is equal to number of moles divided by concentration. So if I'm trying to solve for V now, it's going to be equal to my number of moles. Well, I just calculated that. It is 0.01209 moles. There's my N. 0.01209 moles divided by my concentration, 0.250, and I get a final answer which is 0.0484 liters. Okay, so note that we're back to using C equals N over V. All right, and again, that's on our periodic table. If I pull up my periodic table, we should find C equals, undo. I should find C equals N over V at the bottom of my There it is there, at the bottom of my periodic table. So again, keep that periodic table handy. It is your lifeline for this chapter, for this unit, for this course. Okay, so that leaves us with your turn. So I'm going to leave you with these questions to do here on page 268, and I will take one or two of them up tomorrow before I start the titration. So titration is a procedure that we do in chemistry. It's a lab that we do, or a procedure that we do, and it's a very common and standard procedure. So I'm just going to, very quickly here, it says you will do this lab in any chemistry course that you take anywhere that involves science. Right? They will make you take a first-year chemistry class, and you will do this lab. So really, at the end of the day, that's for any program, right? Anything that involves the body, involves food, involves pharmaceuticals, involves the environment, involves genetics or biotech. You will be doing this. So at the end of the day, I really wish that we could be doing this lab together, because you will need to be able to do it, but we obviously can't. So what I'm going to do tomorrow is I'm going to give you a chance to watch a video of somebody doing the procedure. I'm going to walk you through everything so that you've at least seen it. So when you get where you're going next year, you won't be alone, because the people all over Ontario who are taking 4C Chem this semester aren't getting to do the lab, so they will understand when you get where you're going, but you do need to understand what it is. Right? So I'm going to try and prepare you for that. So, again, back to where we were a minute ago. I will leave you with those questions on page